All right, today we're going to start the first lecture of chapter number 3. And our learning goals for today is represent the position of a body in 2 or 3 dimensions. Second, determine the average and instantaneous velocity vectors of an object. And the third learning goal, find the average and the instantaneous acceleration vector of a body. We'll start with position and velocity vectors, and we'll start with a position vector, and we call it R vector here. Now, in chapter number 2, when we dealt with motion in 1 dimension, we looked at position because your position was along 1 dimension. But here, you can basically look at your position in 2 or 3 dimensions. And that's why we call it position vector. And of course, whenever you write a vector, you put an arrow on top of it to indicate it is a vector. So in 3 dimensions, you can set your axis as X, Y, and I told you can do this in the plane of your screen or the page on your textbook, and the Z axis will be pointing out at you. So this is the 3 axes here, X, Y, Z. Now you can describe your position, and let's take here position P. And this position P has X coordinate, Y coordinate, and Z coordinate. So now we'll treat this as a vector, and that's why we call it here position vector. And we write the vector here, xi hat plus yj hat plus zk hat. Now, in some textbooks, and this is usually common, I will do that as well when we talk about velocity and we'll talk about acceleration. Now, if you have a vector r, you will write it rxi hat plus ryj hat plus rzk hat, meaning when you have a subscript, it means the component here. So it has an Rx, Ry, and Rz. You can find these in some textbook, and we may use this as well in some of our solutions here to indicate that you may encounter this. But in this textbook, since in chapter number 2, we use the position as X, so we write the X component as X, the Y component as Y, and the Z component as Z. And we write our position vector as xi hat plus yj hat plus zk hat. Is this clear? So we're shifting from position to position vector, and we express the position vector by the x, y, and z component. Now, like what we did in chapter number 2, when we looked at position 1 and position 2, and then we talked about a displacement, and we said the displacement should be the displacement from between position 1 and 2, and in that case we said that delta x equals x2 minus x1, where x2 is the second position and x1 is the first position. We're going to do the same thing here, but we're going to talk about delta R. And we say delta R is equal to R2 minus R1. And we deal with R as a vector. So on our x-axis here, this is basically now your position 1, represented by vector R1. And this is position 2 here, represented by a vector R2. So these two vectors represent position 1 and position 2. But if I'm interested in the displacement, which is delta R, where it's going to be R2 minus R1. You know, when you put the tail to the tail, and now this arrow here is pointing toward P2, that's when you're going to have your delta R, where it's equal to R2 minus R1. This is now your displacement vector. Now you can do that, of course, in different times, and that's when we talked about average velocity in the chapter number 2, and we can talk about it here as well. And in this case, the average velocity, it's delta R by delta T, which is R2 minus R1 over T2 minus T1. And R2 here is a vector because it has an arrow on the top, and T1 is a vector because we indicate an arrow on the top. That will give you your average acceleration. Note that when we dealt with average acceleration, average velocity in chapter number 2, we said V F X. And the X there, it meant that you're only looking along one dimension on the x-axis. Now we don't have any component here because this contains all the three components, the X component, the Y component, and the Z component. So you don't see this anymore. But actually you can have your VF, which will have a VF X I hat plus VF Y J hat plus VF Z K hat. And this is basically what we did in the last, or in chapter number 2. So note one thing in the notation here, we're not putting the component because this vector contains all three of them. So that's one thing that you have to note here, and how this is how we calculate the average velocity. Now, what is the direction of this average velocity? Okay. Well, the time here is a scalar, but delta R here is the vector. So the direction will come from the direction of delta R. And that's why we say here that the direction of your average velocity vector is in the same direction as your displacement vector, delta R. So if you look at the graph that we have here, that's the average. And you can see the green arrow here, which basically describes your velocity. Okay. And that's why we say that this velocity vector is along delta R. Now you can, and we'll discuss later on, that's the path of the particle. It doesn't have to, you can have the blue path here, and you're choosing P1 and P2. Okay. But my average velocity will be the direction of delta R here. That's why it is represented here by the green arrow. But that basically, knowing position vector at P2 does not tell me anything about velocity at P2. And we already dealt with this in chapter number 2. When we talked about average velocity doesn't tell me, okay, what is the instantaneous velocity at position 2 or position 1. I'm just taking the average between both of them. So that's now what the average velocity vector is. Now I want to get to the instantaneous velocity vector. And the instantaneous velocity vector, like what we did in the previous chapter, chapter 2, we'll take it in the limit as delta t goes to 0 of delta r over delta t, which is equal to dr by dt. Meaning that I will take the v1 as tangent to the path at p1, and that will be basically going to be my instantaneous velocity vector there. And at p2, I will take the slope of this line, which is tangent to my path, and that's v2. That's instantaneous. So in the previous slide, we talked about average velocity. And average velocity, it just tells me the average between these two positions, but it didn't tell me what is the velocity at position 1 and position 2. If I want to know the velocity at position 2 or position 1, I have to look at the velocity at that instant, at that time, at that position, which we call instantaneous velocity, and here we call it velocity vector because it is in 2 or 3 dimensions. And it should be the limit as delta t goes to 0 of delta r over delta t, which is equal to dr by dt. So that's the instantaneous velocity. Direction now is what we say here. It is tangent to the path. That's why v2 is tangent to p2 here, and v1 is tangent to p1 here. And like in the previous slide, we said the average velocity is in the direction of the displacement, which is delta r. So this is one thing that you have to keep in mind here. And then we say the magnitude of the velocity vector, we call it the speed. So the speed here will be the absolute value of v. Remember what we did in the previous chapter. I told you that v should equal to the absolute value of x, because at that time we're only dealing with velocity along the x-axis. But here we're looking at a velocity vector. So v here as a symbol, I don't write an arrow on top of it to indicate it is a vector because I'm dealing only with the magnitude. I don't write any subscript to indicate it is a component. By the way, I can write a subscript where I say P1 or P2 or 1 or 2 indicating at that position or that time, but not to indicate it is what it is, a component like what we did in the case of X, or when dealt with it in the free fall, we said it is the absolute value of the Y component. So this is something that you have to keep in mind. Now, if I look at V here, which should equal to dr by dt. And you know that we wrote r as x I hat plus y j hat plus z k hat. So my v here will be d by dt of x I hat plus y j hat plus z k hat. So v here will be dx by dt I hat plus dy by dt j hat plus dz by dt k hat. This, of course, will be vx. This will be vy. This will be vz. So you will write your velocity vector as vx I hat plus vy j hat plus vz k hat. That's your velocity vector. If I write it this way, that means I'm interested in the speed. And the speed is the magnitude of this vector. And the speed is the magnitude. So when you write you want to calculate that, it will be Vx squared plus Vy squared plus Vz squared. We don't put a plus or minus here because I'm interested in magnitude, and the magnitude has to be positive. So I'm taking the positive root only. And that basically gives my speed, and that's why you say the speed here is the absolute value of my velocity. So that's how we look at average velocity vector, which is delta r over delta t, or we look at instantaneous velocity vector, which is dr by dt. Is this clear? So this is basically, again, to represent what a instantaneous velocity vector is dr by dt, which is dx plus dx d of xi hat plus yj hat plus zk hat by dt, which will give you dx by dt I hat, dy by dt j hat, or dz by dt k hat, which will give you vxi hat plus vy j hat plus vz k hat. Now we can look at a velocity vector in 2 dimensions. So that's your velocity vector here in 2 dimensions, and it will have an x component, a y component. So in this case, we can write v as vx I hat plus vy j hat. And if you want to get the magnitude of that vector, which is equaling the speed here, it will be the square root of x squared plus y squared. And that will give you your speed now. So there are 2 things we can say here. We can say the speed or the magnitude of the velocity. And it has these. Now remember here, v, we use the symbol v and we put a subscript x to denote it's the x component of the velocity, and v and subscript y to denote it is the y component of your velocity. But when we dealt with your vector r, we wrote x, y, and z. That's what we use in this textbook. But we can also write r as rx I hat plus ry j hat plus rz k hat. That's usually the normal way of when you write a vector. You use the same symbol and you put subscript x, y, z to indicate that these are the components of the vector. So in this case here, we calculate the speed. Now you want to get the direction, and remember what we talked about the direction. We said usually we take tan alpha y component over the x component, meaning that alpha here will be tan inverse of vy over vx. And that will give you the angle relative to the positive x-axis. Remember the rules. We talked about if you are in the first quadrant, you add 0. That means you do nothing. If you are in the second quadrant, you add 180 degrees. If you are in the third quadrant, you add 180 degrees. And if you are in the fourth quadrant, you add 360 degrees to get your angle relative to the positive x-axis. That's if you're dealing with a vector in 2 dimensions here. Just to refresh your memory of what we did. So speed is the magnitude of your velocity. Now let's deal with some examples here, and the first example is 3.1, and it tells you that you have a robotic vehicle is exploring the surface of Mars. The stationary Mars lander is the origin of the coordinates, and the surrounding surface lies in the XY plane. The vehicle, which represents as a point, has the coordinate x equal to minus 0.25 t squared, and y is equal to 1.0 times t plus 0.025 t cubed. So they gave us the x component as a function of time. Okay, so we can write here x of t, and the y component as a function of time. They ask us find the vehicle's coordinates and distance from the lander at 2 seconds. So they want the coordinates, and they already given me the coordinates as a function of time. So at 2 seconds, I'm going to look at x of 2 seconds. Well, 2 stays as it is, but I have 2 squared here, and 2 squared gives me 4, and 4 times 0.25 will give me 1, and 2 minus 1 will give me 1 meter. So that's basically now your x at 2 seconds. Y at 2 seconds, it tells you that t is 2, and 2 times 1 will give you 2, and 2 cubed will give you 8, and 8 times 0.025 will give you 0.2. So you have 2 plus 0.2, and it will give you here 2.2 meters. So we have the x and the y coordinate. Now you can write your position vector, which has 1 I hat plus 2.2 j hat, and the units, of course, are meters, and this is now your position vector. Now they ask you for the distance, and they told you that it started from the origin. So you're going to look at the distance between the origin and these x coordinates. So if you want to do that, well, relative to the origin, you are at x equal 1, and y is equal to 2.2. So if this is your x and this is your y, you're basically having 1 and probably 2.2. So this is basically the distance here, which will be the square root of the x component squared plus the y, or the x coordinate squared plus the y coordinate squared, and that's why we have here r is equal to rx squared plus ry squared. And again, I told you different textbooks, they usually use the same letter for the vector, and they put the subscript x and y to denote its x and y component. In this textbook, when we come to the position, we always write x, y, z, but we write r for the vector. So just be alarmed if you see a textbook using these. In this textbook, we usually use R1, R2, or X1 and X2. In some textbooks, they always use F and I, F meaning final and I meaning initial. It's the same thing. Okay. So 1 squared plus 2.2 squared, and you get here 2.92 meters. Okay, and this is basically the distance of your vehicle from the origin. The same example again, but in B here, they ask you for the displacement, and right away, you know, when the displacement, that means have between two different times, and the average velocity vector between t equal to 0 and t is equal to 2 seconds. Now, you know right away that our definition for average velocity equals delta R by delta T, where delta R should be equal to R2 minus R1. Here we use delta R equal to R final minus R initial, which is 2 minus 1. So what is our R initial and what is our R final? Okay. The R initial at t is equal to 0. And R final is at t is equal to 2 seconds. So now I want to evaluate my R initial at 0. So I will look at the x coordinate. If I say 2 minus 0.25 times 0, that will give me 0. So the x here will equal to 2. The y, I have t here and I have t here. You put 0 here, you put 0 here. The y will equal to 0. So your initial vector r, or r at 0, it only has an x component, and that's why we say it is 2i here. I hat. And of course, we put the units here, which is meter. Now, I want to look for the vector at 2 seconds. Okay, so I want to look at R final. Now, R final here, if I put 2 seconds, so 2 squared here will give me 4, and 4 times 0.25 will give me 1, and 2 minus 1 will give me 1i. Okay, so I have 1i hat here. For the y, I have 1 times 2, which is 2, and I have here 2 cubed, and 2 cubed will give me 8, and 8 times 0.25 will give me 0.2. So here it will give me 2.2. So I'll have here plus 2.2 j hat. So now if I want to take the delta R, I will have I hat plus 2.2 j hat. That's your first vector, minus the second vector, which is just basically 2i hat. So I hat minus 2i hat will give me minus I hat, and 2.2 j hat, and I have no j hat, so it will be plus 2 j hat. That's basically your delta R. The average velocity is delta R by delta t, which is minus I hat plus 2.2 j hat over 2 minus 0. And of course, 1 divided 2 will give you 0.5. So you get minus 0.5 I hat. And 2.2 divided by 2, it will give you 1.1 j hat. And of course, the units here is meter per second. Is this clear? So that's how we deal with displacement and average velocity. The same example, but in C here, they say find a general expression for the vehicle's instantaneous velocity expressed at 2 seconds in forms of component and in terms of magnitude and direction. So now you know that your velocity should have an x component plus a y component, and the x component should equal to dx by dt, and the y component should equal to dy by dt. So the vx, which is dx by dt, you go here, you have no t here, so you get 0, and you come here, the t squared will give you 2t, 2 times minus 0.25, it will give you minus 0.5 t meters per second. Vy, which is equal to dy by dt. Of course, when you take d by dt of t, you get 1. That's why you have 1 here. And when you take d by dt of t cubed, you get 3t squared. And 3 times 0.025 will give you 0.075 t squared meters per second. So your vector, velocity vector now will be minus 0.5 t I hat plus 1 plus 0.075 t squared j hat meters per second. That's your velocity vector. At t is equal to 2 seconds now, if you look at your Vx, you put 2, it will give you minus 1 meters per second. At 2 seconds, if you put it in the Vy, t 2 squared there will give you 4. 4 times 0.075 will give you 0.3. So 1 plus 0.3, and you get here basically the Vy, which will equal to 1.3 meters per second. So your velocity vector now at 2 seconds, it's equal to minus 1 I hat plus 1.3 j hat meters per second. You can get your speed, which will be equal to the square root of minus 1 squared plus 1.3 squared. You can calculate that. You can also get your direction. You say alpha equal tan inverse of y is 1.3 and x is minus 1. Right away, you know that you are in the second quadrant because your y is positive, your x is negative. So whatever value you get out of here, you're going to add to it 180 degrees to tell you that you are in the second quadrant if you want to get your angle relative to the positive x-axis. So this is now how we apply the concept of instantaneous velocity vector or average velocity vector or position vector in 2 dimensions. Any questions before I move on? Now, the concept that we want to deal with next, which we did in the last lecture, but here we're going to talk about acceleration vector, okay, instead of acceleration only, because in the last lecture we dealt with a fx, and we said that this is equal to delta vx by delta t, and we dealt with ax, and we said this is dvx by dt. That's in 1 dimension. Here we have to deal with it in 2 dimensions. So imagine if you have a path like this, and this is position 1, and the v1 here will be tangent, okay, to it, like it's the car is moving here, so that's p1, and you take the v1 as tangent to this curve here. Now you go to second position, and the v2 will be tangent to it. Now you want to get your average acceleration, and again I remind you, we don't have dash x here because you are dealing with 2 or 3 dimensions, so you don't have to put that, there will be inside, which equal to delta v by delta t, which should equal to v2 minus v1 over t2 minus t1. So if I want to get v2 minus v1. I can bring this vector here, so they are tail to tail. And this is your v1, and this is v2, but you want to get v2 minus v1, so you basically put the arrow of delta v pointing toward v2 to get v2 minus v1, and that basically gives you your velocity vector. That's another way. You can add the two vectors together, so you can take this vector, you multiply it by -1, you invert it, and then you bring the tail to the head, like what we did in chapter number 1 when we talked about vectors, and that's basically your delta v. Okay, so it's in the same way. So this is now your average acceleration. Now, or we say the average acceleration vector. What is, or where is the direction of this vector? Well, it has to be in the direction of delta v. So we say here the direction of AF is in the same direction as delta v. But now we want to deal with the instantaneous acceleration vector. Okay. And the instantaneous acceleration vector, we take it in the limit as delta t goes to 0 of delta v by delta t, which is dv by dt. Now this is instantaneous. Now you may come here and you ask about the direction. In the previous slide, we said the direction of the average velocity is in the same direction as delta v. But where is the direction of the acceleration here? So now, at position 1, we said that the velocity v1 should be tangent to the curve. And in position 2, v2 should be also tangent to the curve. But the acceleration now works on changing the velocity. So I have a vector that's basically pointing this way, the vector is pointing that way. A vector, as we discussed in chapter number 1, it has two things. It has a magnitude and direction. And you can change the magnitude, or you can change the direction, or you can change both of them. Now, in the case of changing our velocity, we need acceleration to do that for us. And this acceleration can change both. It can change the magnitude, or it can change the direction. So in the situation that we have here, okay, it is a curved path, and it's going to change direction. So the acceleration cannot be parallel to it. It cannot be in the same direction. Okay. And that's why the acceleration here is pointing toward the concave of the path in order to change its direction. So that's one thing that you have to be careful with. Now, when we dealt with the instantaneous acceleration vector, we said it's delta v by delta t. And v, of course, has an x component, y component, and z component. So your v as a vector has vx I hat plus vy j hat plus vz k hat. So if you want to take delta by delta t of this, then you're going to have for ax dvx by dt, ay d, this arrow here should not be there. I apologize for that. dvy by dt and dvz by dt. And the a here will be ax I hat plus ay j hat plus az k hat. And that's now your acceleration vector. And like what we did in chapter number 2, we only looked at either AX and VX, or we dealt with VY and AY if we're looking along the Y direction when we said that this is the free fall. And here, no, the vector will have the X, Y, Z components. And the acceleration vector can change the velocity by changing two things. It can change the magnitude and direction. It's the same example that we dealt with, 3.1, but now they ask us here to find the components of the average acceleration between t0 and t2 seconds. We already done previously that Vx should equal to dx by dt, which is equal to minus 0.5t, and Vy is equal to dy by dt, which should equal to 1 plus 0.05 t squared. But they want the average acceleration between 0 and 2 seconds. So I have to evaluate, because I know that my average acceleration should be equal to delta V by delta T, which is V2 minus V1. So what is my V1 and what's my V2? V1 is at t is equal to 0, and V2 is at t equal to 2 seconds. So at t is equal to 0, the V1x, and the 1 here, meaning that at position 1, which is 0. And x meaning the x component. So it's Vx of 0, and it gives you 0 because you put t is equal to 0, it will give you 0. The Vy, it is 1 plus 0.075 times t squared, and the t is 2 here, so 2 squared will give you 4. 4 times this will give you 0.3. And this basically, you put 0 here, so it will give you 0, so you end up with 1. So when you look at V1 here, and the subscript 1 here, that means V1, the initial position, not meaning any components or anything, and it will give you plus j hat meter per second. T2, that means I'm putting t is equal to 2. You put 2 here, you will get minus 1 for Vx. You put 2 in t squared here, so it is 2 squared is 4. 4 times 0.75 will be 0.3, and it will give you 1.3. So your V2 now, it's equal to minus I hat plus 1.3 j hat meter per second. Now I want to look at delta V, which is V2 minus V1. V2 is minus I plus 1.3 j hat. V1 is 0 I hat plus j hat. So if you do that, you will get minus I hat, and 1.3 j hat minus 1, it will give you 0.3 j hat meter per second. That's your delta V. If you take the average, which is delta V by delta T, it will be minus I hat plus 3 j hat divided by 2. And that will give you minus 0.5 I hat plus 0.15 j hat meters per second squared. And that's how you obtain your average acceleration. That's basically a straightforward application of what we learned of the average acceleration. In D here, they ask you to find the instantaneous acceleration. Instantaneous, that means at certain time, at 2. Now, we obtained our Vx as equal to minus 0.5 t, Vy as 1 plus 0.075 t squared. I want to get my instantaneous. My instantaneous, that means I have to take the derivative. So I'll have the x component of my instantaneous acceleration as dvx by dt. And when you take d by dt of minus 0.5 t, of course, the derivation of t with respect to t will be 1. And you will get here minus 0.5 meters per second squared. The ay will be dvy by dt. So the 1 here will become 0. The t squared here will give you 2t. And 2 times 0.075, it will give you 0.15 t meters per second squared. So now you have your x component and y component. So your vector here will equal to minus 0.5 I plus 0.15 t j hat meters per second squared. Now you want to evaluate that at 2 seconds. Now at 2 seconds, AX will stay the same because it's still minus 0.5. It's a constant. But AY, you put 2 there, and 2 times 0.15 will give you 0.3. So your acceleration or the acceleration vector at 2 will equal to minus 0.5 I hat plus 0.3 j hat meters per second squared. Is this clear? Any questions so far? Okay. So that's how we basically apply these concepts. So in the previous chapter, we looked at position, we looked at average velocity, instantaneous velocity, and then we looked at average acceleration, instantaneous acceleration, but it was done in one dimension. Today, we're dealing with it as a position vector, velocity vector, acceleration vector. It is the same concept, but we're extending that to 2 or 3 dimensions. Now, one thing that you have to be careful with when you want to change your velocity. The velocity is a vector. And when you have a vector, it has a magnitude and direction. So you can either change the magnitude and you keep the direction as it is, or you can keep the magnitude and change the direction, or you can change the magnitude and change the direction at the same time. And we already discussed, if we want to change our velocity, we must have acceleration. So the acceleration is going to do that job. It's going to change my velocity vector. So there is the magnitude that I can change, and there is the direction that I can change. So if I look at a curved path like this, and I have an object that's basically at this position here, and we said that if I want to get the instantaneous velocity, it is the tangent to this point here. But of course, you will go on this curved path. So definitely you're going to change the direction. And you can also change the magnitude. And that's why here we talk about parallel and perpendicular components of the acceleration. That happens when you have a curved path. Parallel, that means either along the direction of your velocity or opposite to it, and that can change the magnitude of your velocity, which is the speed. And then if you want to change your direction, something has to pull toward the curve, And that's why we call this the perpendicular component, which is responsible for changing your direction. And that should pull toward the focus or the center of the curvature. So you have both of these. So we have here what we call tangent to the path, which will be along the velocity. It will be parallel to the velocity. And that's responsible for changing speed only. And you have perpendicular to the tangent of the path. And this is basically responsible for changing direction. So when you go around the curved path, okay, your acceleration will have these two, parallel component and perpendicular component. One is changing the magnitude, the other one will be changing direction. So in this way, if I want to write my acceleration vector here, I can write it as A tangential or parallel plus A perpendicular to the velocity to change its direction. And of course, A will be the resultant. You have two vectors here, and you're getting the resultant of these two vectors. So if I want to take the magnitude of A here, it will be the square root of A parallel squared plus A perpendicular squared. If I want to get a direction relative to what? So in this situation here, you want to measure it relative to the position, so you may want to make it relative to this tangent curve, and that's why we can say here that tan alpha will equal to A perpendicular over A parallel, and you're measuring this angle here relative to this tangent, and that will be your resultant acceleration here. Now, if you're moving along straight line, then the perpendicular component will cancel and your acceleration will be along V. If you're moving along a circle with constant speed, that means you're not changing the magnitude, then the A parallel will be 0 and you will be just, the acceleration will be toward the center. Now, if you're given the acceleration and you're given the velocity vectors, you can figure out the angle between both of them. Remember when we said about dot product, when you have A dot V, it will be AV cosine alpha, where alpha will be the angle between both of them. So if you're given the vector of A and the vector of B, you can figure out the alpha between both of them by saying that cosine alpha will be A dot V divided by AV. And of course, alpha will be the cosine inverse of A dot V divided by AV. And if you know the magnitude of your acceleration and you know the angle alpha, you can figure out the A parallel, which will be A cosine alpha, and the A perpendicular will be A sine alpha. So when you have a two-dimensional motion like this on a curve, then you can basically change both magnitude of your velocity, the direction of your velocity. The velocity, if you want to change its magnitude or speed, the acceleration should be parallel to it along the direction or opposite to the direction if you want to slow down. And the perpendicular component of the acceleration is there to change your direction. Is this clear? So if you only changing the magnitude of your velocity, which is the speed, well, in that case, your perpendicular component of the acceleration is 0 because you're not touching the direction. And the velocity vector and the acceleration vector are parallel to each other. They could be anti-parallel in the case when you're trying to slow down. Okay. Now, you can also do a change in the direction only. That means your speed is kept constant. And remember what I told you about your acceleration should be parallel plus perpendicular. But if this is equal to 0, it's cancelled. So your whole acceleration is just perpendicular, which in this case will be pointing toward the center of the focus of your curvature to make you go around what? Around a circular path. And this is the case when you have a constant speed. So a note here, when you go around the circular motion, if you go around the circle this way, definitely you're going to change direction when you go around a circle. So the velocity vector is not going to be constant because you're changing your direction. But you can keep the speed constant. So it is right to say that you can go around a circle with constant speed, and that's what they call uniform circular motion. But it is wrong to say that you can go around a circle with constant velocity. Because if you want to go around the circle, you're forced to change the direction of your velocity. Is this clear? Again, you can go around a curved path and change both. You can change the magnitude and direction. So in this situation here, you have your velocity vector and you have your acceleration vector. And this acceleration vector will have a parallel or tangent component, and it will have a perpendicular component. Parallel is changing the speed or the magnitude of your vector. Perpendicular component is changing the direction of your vector. In this case here, the acceleration is, or the tangential or parallel component is along the velocity, and you are speeding up. If you look at the situation that we have here, now this vector here will have an A parallel in this direction here, and A perpendicular in this direction here, and your A tangent or A parallel to the velocity is opposite. And in this case, you're going around the curvature, but you are slowing down. So you can go around the curved path and you change both velocity and velocity. You can change the magnitude of velocity, which is the speed, and direction. Is this clear? Any question on this? So in this example here, for the example that we have in 3.1, and they ask us find the parallel and perpendicular component of the acceleration at 2 seconds. Now, this is our acceleration that we did previously at 2 seconds, which is meters per second squared. And this is our velocity at 2 seconds, meters per second. And they want us to find the components. Remember what we said. We said that in the previous slide, A parallel should equal to A cosine alpha, and A perpendicular should be equal to A sine alpha. So we want to find alpha. And I told you that alpha should equal to A dot V over AV, where A here is the magnitude. So we take the magnitude of A, which is the square root of 0.5 squared plus 0.3 squared, and it gives me 0.58 meters per second squared. And I can take the magnitude of V, which is 1 squared, or minus 1 squared, plus 1.3 squared, and that will give me 1.69 meters per second. So these are the magnitudes. And I can take A dot V, and A dot V, I'm dotting A with V, so I'm dotting minus 0.5 by minus I, and I dot I is 1, minus times minus is 1, so I get 0.5. And when I dot 0.3J with 1.3J, so J dot J is 1, and 0.3 times 1.3 will give you 0.3. And then you look at your A multiplied by V, which is 0.58 plus 1.69. That will basically give you alpha, which is the cosine inverse of 0.89 over 0.58 times 0.169, and it gives you alpha equal to 20.6 degrees between the velocity and the acceleration. Now you can get your parallel component, okay, which happens to be here positive, and you get your perpendicular component of the acceleration. Now you know right away that this is positive, which means along the velocity, and in this case, it is what it is, speeding up. So you have to be careful when you are moving in 2 or 3 dimensions, especially when you go around curved path. It's like a circular motion, and you really have to look at your acceleration in this sense, perpendicular and parallel component. Parallel component works on changing the speed, and perpendicular component works on changing the magnitude. Is this clear? Any question on these? We have a few 3 questions here to work on. And the first one here, they give you a figure. This illustration shows the path of a parabolic robotic vehicle or rover. What is the acceleration of the rover's average acceleration vector for the time interval 0 to 2? So this is your vector here at t is equal to 0. And this is your vector here at t is equal to 2 seconds. And you want to get your average acceleration. And you know that the average acceleration, it's delta v by delta t. So you're going to bring this vector up here. That's basically your v0. And then you want to get the delta v here. So if you look at delta v here, you will find that it's pointing toward the left, and it is what it is up. Is this clear? Now in this question here, they give you a motion diagram, shows an object moving along a curved path at constant speed. So they tell you it's constant speed. At which of the points A, C, and E does the object have 0 acceleration? So it's a curved path like this. You know your acceleration will have a parallel component and a perpendicular component. Parallel component is responsible for changing magnitude. Perpendicular component is responsible for changing direction. Now they tell you it's constant speed, and if it's constant speed, then this is 0. It's not there. They ask here, they want to have 0 acceleration. That means they want A parallel also equal to 0. And when you look at these points, at this point, you're going around the curve. So you're going to change direction. When you go around this point, you're going around the curve. You're changing your direction. So these points, you cannot have a perpendicular equal to 0. But at this point here, you're moving along straight line. You don't need to change direction. And that's why we say at point A, C here, the acceleration is equal to 0 because you're moving constant speed. Your A parallel 0. And of course, you don't need A perpendicular to change your direction. And that's why the answer here is B. And in question 3 here, they give you the velocity and acceleration of an object at certain instant. So V is equal to 3 meters per second J hat. A is equal to minus 0.5 meters per second I hat minus 0.2 meters per second J hat. So your acceleration here has X and Y component. Your velocity here has only a Y component. So if you look between the acceleration and the velocity, you will say, well, to the velocity, there is a parallel component along the J, and there is a perpendicular component along the A. So this part will work on changing the direction of your velocity. This part here will work on changing your magnitude or speed, and of course, since it's minus, that means it's opposite to you. And that's why we say that you are slowing down and following a curved path here. So you should basically look at them in this way. Any questions so far? Is this clear of how we deal with this? So to conclude, in chapter number 2, we looked at position, and then we looked at velocity, and then we looked at acceleration. Today, we're going to look at 2 and 3 dimensions. So we look at position vectors, and we look at the displacement, which is delta R, which is R2 minus R1. We looked at average velocity vector. We looked at the instantaneous velocity vector, and then we looked at the average acceleration, and we looked at the instantaneous acceleration. And I told you, you have to be careful when you go around a curved path. One thing that I want to add here as well, when we talk about acceleration, remember we said that R is equal to X I hat plus Y J hat plus Z K hat. And we said that V is delta R by delta T, which basically was equal to delta X by delta T I hat plus delta Y by delta T J hat plus dz by dt k hat. Now, your acceleration is dv by dt. So it's basically d by dt of dxi hat plus dy by dtj hat plus dz by dtk hat, meaning that a also is the second derivative of x with respect to I hat plus the second derivative of y with t j hat plus the second derivative of z by t k hat. This is just, I mean, you can also take the second derivative of position relative to time to also get acceleration. Is this clear? Any questions on this? Good.